Hello everyone, my name is Paszke, and today I want to tell you a bit about my joint work with Ningning, who's also at Google DeepMind, about a new version of record types, a new record calculus with a particular focus on typing and analyzing tabular data analysis. So just to give you a bit of a background, I'm in a team that works on a numerical computing library called JAX that is embedded in Python. And Ningning collaborates with us, and so our group actually mostly focuses on programming with multidimensional arrays. But we also like to sort of sometimes think about other things. And tabular programming always seemed very close, and yet like a little different than multidimensional array programming. But we figured, we want to think about this more. We do like type systems. We have another research project in a research language called DEX, which where we essentially designed a typing system especially for multidimensional array programming, but at the same time designing a library in Python, we do actually understand a lot of our users wouldn't necessarily agree, and they wouldn't want to have an overly complicated type system. But at the same time, we do see a lot of users wanting static analysis. They want to see how the shapes of the arrays and their data progress and the types change as they write their analysis. So the question here is, can we design sort of a lightweight system that will allow us to answer those questions and do a very lightweight formal verification of essentially code that operates on data frames? So now, one interesting project here, as I mentioned, we're not experts in data frames, but there is the Brown benchmark for tabular types, which is a very interesting development. It essentially summarizes a number of scripts that have been put up online that do data analysis into essentially a little benchmark for what kind of tables you should support, what kind of functions that manipulate tables you should support, and what kind of errors you could be potentially catching. So this is what we will use for evaluation at the end. And so as a starting point, we took, essentially what we kind of consider a bit as the archetype of a table language, which is SQL. And the first thing you do in SQL oftentimes is you create a table, right? And if you look at what you specify when you create a table, it's essentially a collection of heterogeneous fields that you can access by name. And if you translate this to the language of type theory, perhaps that starts looking very similar to record types. And so that's what we ended up looking at. But one conclusion we ended up with is that actually a lot of the record theories either end up a little too constrained, or they end up being very complicated, perhaps with an extensive use of qualified types that we feel just would be a little difficult to explain to users. And it might just get a bit in the way of them successfully just writing some program to summarize some experiment. So to summarize this talk, there will be three parts. First, we'll go over an informal sketch of our calculus. Then we'll go over the formal definition of our language and the formal results. And finally, we will see the evaluation section to see how it does on the Brown benchmark for tabular types. So we'll start with the informal sketch, as I mentioned. In the first step, you can think of records essentially as sort of tuples with named fields. So in here, you can see a record type. It has three fields: length, height, and width. They all have the type int. Now, at this point, the only record operation that we really care about is projection by name. Notably, you cannot project by position, and that is because we identify records up to field ordering. It doesn't really matter in which order you declare the fields in a record or in its type. They can be freely permuted, and they will be considered equivalent. Okay, so next step is to allow something similar to structural subtyping. This is a very standard calculus for records at this point. The idea is that now you not only are able to declare the sort of fields and types, but you can also say, and then there is a row. So essentially another sort of set of fields in the record that you will just completely ignore in your polymorphic functions. And this allows us to, for example, apply area to records that have height and width, but then of type int, both, but then also like an arbitrary suffix of other fields that get ignored. Now, there is an interesting question, though, which is what happens if this polymorphic tail actually gets instantiated with a pre-existing field name? What if the row here actually does contain the field width or height? And so usually what most record theories do at this point is they will reach to qualified types to essentially encode constraints such as the extension cannot contain height and it cannot contain width. Now, we didn't like that very much, and we found a solution in one of Dan Leyen's papers. And that is to allow scope labels. So essentially records now do allow duplicate labels. As you can see here, the record has duplicate field L, but the fields shadow each other. So now the order starts to matter a little bit. When you project L from the record like this, you get back the integer 2. To access the second field, you actually first have to delete the field L from the record, which will remove this one, only leaving a record with this component. And then as you project L again, you will back the field of type string. This is a valid program. And again, as I mentioned, records are not completely unordered anymore. The fields of distinct names can still be permuted freely, but within a single name, the order of fields matters because it does change the shadowing. Okay, and the next extension is first class labels and rows. So essentially what we have found is that it's also often useful to be able to treat those names as first class values. You want to write a function where the user says, get me a value of this column, and the column name is passed as a value. And so this is essentially what it is. We're adding singleton types for field labels and for record rows. Now, one nice property of this is that record field projection can be assigned a proper type. You can see that here it essentially is a function that says for any label, for any type alpha that this field will have, and for any row afterwards, if you give me a record that has this field L of type alpha and then row, and then you specify the L explicitly, which we will discuss later, I will give you back the sort of value of that field, which will be of type alpha. Now, an interesting problem arises again. Consider this function here, which says if you give me any label and then a record that has a field of that label in type string and then a field of type foo of int, and the program essentially just accesses foo from that polymorphic record. The question is, what will be the type of that? And in our theory, we actually reject this, right? And this is because if L gets instantiated at foo, the type should be string. But if L gets instantiated at anything else than foo, then actually the type should be int. And so that's why the program is rejected. We kind of cannot infer that statically. If you really wanted to access the field foo, you would have to do what we did before. So you would have to explicitly first delete the field L and then access foo. So essentially an interesting thing here is that essentially first class fields, once you do allow scope labels, and to the best of our knowledge, this might as well be the first place where this is done, you do have to consider those first class fields with first class labels to shadow all of the subsequent fields, because you kind of cannot reason yet about their shadowing semantics. And so that constrains even more the permutations you can apply to record fields. Okay, and finally, the last operation we add is record concatenation. So you can essentially take two records and kind of splat them together, all of their fields. The interesting part is that now you can essentially write records that arbitrarily interleave extensions with rows and with labels and with fields where the labels are first class or just literals. And another two interesting operations are perhaps row projection, which essentially just restricts the record to one of its sides. So you essentially drop a bunch of fields. Okay, moving on to the second section, we'll now discuss the formal results. So in here we have defined essentially a model language, which you can see here. Essentially in the first row, it's just fairly standard lambda calculus with let bindings. In the second row, you can see the record constructors, you can see the label singleton constructor and the field projection operator. In the third row, you can see the row constructors, you can see the row projection and sort of deletion from the record. Now, since we've based this on essentially polymorphic lambda calculus, the type system we specify is an extension of the Hindley-Milner style polymorphic type system, which for most of the language is standard. We do specify the rules for all of those new constructs, although they are not that complicated. The two most interesting parts, I think, is that we had to add this rule, which essentially lets you cast the type of a term to another type for as long as they are considered to be equivalent under this equivalence relation, which basically says, again, they might differ by permutation of the fields in records for as long as they are valid, right? So it encodes things like concatenation of rows is actually an associative monoid. It's just a monoid, and empty row is the neutral type. And also, it encodes the details of field shadowing and when they can be reordered. The second interesting rule is the variable rule where, you would have to, if it has a sort of polymorphic polytype, you might need to instantiate it. And so we actually restrict the instantiation a little for variables that correspond to labels or rows. And so if you take this as an example, so E is an expression of type for any label A, it will give you back a record with a field labeled by A of type int, and then L2, which is a literal of type bool. And now you can ask what will be the type of E.L2. And the problem here is that depending on the instantiation of A, you might end up answering int if you instantiated A to L2, or you might end up with bool if you instantiated A to anything else, right? So we essentially constrain instantiation to only allow instantiating variables that allow in sort of the tail position of the record. Again, for more details, I unfortunately have to redirect you to the paper. Okay, and the final component of the formal part is the type inference algorithm. We do extend a Hindley-Milner style type inference scheme. We show that our type inference procedure is sound. We do discuss that the system actually lacks the most general unifiers. This has been a known problem that's also discussed in the paper that introduced scoped labels. Essentially, already at that point, you start losing that property. You can see that if you try to unify, a row like this with a row like that, you can sort of use this component to unify with this and that with the second part, or you can swap them. And since L1 and L2 are disjoint labels, both will give you valid solutions. Now, as a silver lining, when inference does succeed, we actually do show that it does return the most general unifier. And sort of very practically, we in our evaluation, we actually haven't found any cases where that would be a problem. And that's probably because actually this unification problem is very unnatural from the point of view of our system. It can happen, but it's very unnatural, right? And that's because to instantiate the inference variables alpha and beta, beta is okay because it's in tail position, but recall the tail check, we normally would not instantiate alpha at the front. So that usually only happens when there's another argument, such as an explicit label, that would specify alpha, and essentially given that label, inference would still have enough information to succeed on this program. All right, we get to the final evaluation section. As I mentioned, we will be looking at the Brown benchmark for tabular types. We evaluate our solution on we don't have a concrete implementation. We have a very early prototype, but that was way too early to put in here. So we evaluate assuming a Haskell style language that is extended with our record type operations. In particular, we assume existence of some types like maybe, and then arrays or list types allowing arbitrary types inside. And we will not be talking about implementations of methods since this language is entirely hypothetical. We will focus only on the typing discipline. So tables, this is the first step of the benchmark. As we mentioned before, a table is essentially an array of records. Now, one big deviation from the benchmark and a requirement we fail is that the benchmark does require columns to be ordered, which they're not here, and it does require them to be unique, which again, they are not. Column shadowing can potentially lead to bugs, but we still find it as an acceptable sort of trade-off, given that we can essentially end up with a significantly simpler type system. And here you can see the types of the tables from the benchmark, but unfortunately I will not have the time to get deeper into this. Here is a summary of all the functions except for the functions that only modify rows, like permute the rows of a data table, for example. Those have nothing to do with columns, and so with our record types. So here we only focus on the ones that actually are relevant. You can see that for most of them, we actually do succeed to do pretty well. There are some exceptions, like for example, get column, in the benchmark it should also work on positional indexing, and here we can't. Rename columns, for example, it can let you rename multiple columns at the same time. In our case, we can only type a version that renames a single column, but luckily renaming multiple columns, you can just get it by composing the function that renames a single column multiple times, so hopefully it should just work. One interesting example, just to give you a sense of how this works, is left join. Essentially, a left join, if given a table, two tables like this, what happens is that it sort of takes the left table unmodified, and then it looks at the key column and here ID, and it tries to look up the values in the right column. If they are there, then it just puts them in the extra column. If not, they are missing. Now, we cannot just type this directly because we don't allow missing values in arbitrary places, But you can see from this type that you can actually resolve this fairly easily, right? You have here the one data table with the key columns and value columns, another one with key columns and other value columns. You specify explicitly what the key set of columns should be, and then in the result we just copy the left record as it was, and then we attach an extra field which is an optional value of all of the value columns from the second record. Okay, and about static reasoning and error checking, essentially all malformed tables that the benchmark lists are rejected by our systems. When we looked through the example errors, most of them were because programs were accessing columns that just didn't exist, and in our type system that is also caught. Array length checks are kind of independent, so again, depends on your array type. And again, disjointness constraints cannot be enforced. But I think still, like, we want to stress that, checks are an added thing here. I think just the most important part is that we can track the progression of the shape of the data. Finally, just to quickly discuss the negative results. So one group was table pivots. That's essentially a group of functions that take a number of homogeneously typed columns and flatten them into two columns, one with column name and another one with value. That's kind of a complicated operation to type, and we didn't find a sufficient solution here. Outside of the benchmark, there are also a few interesting points. One is about type classes for records. Sometimes we would like to do record equality, and there is a question of whether we can integrate this into existing type class systems. Records are not really built inductively, right? Because there are multiple potential definitions, because field ordering doesn't matter that much. If you're interested, please do please do take a look at the paper. Schema reflection is another one. Can you get a list of labels of columns? Right now, we don't have a great answer for that. And finally, I do think that there are some limitations of using singleton types as as sort of calling them first class labels or rows. I do think that they are still fairly limited, but again, due to time constraints, unfortunately, I will have to skip that discussion. Okay, just to conclude, we did present a novel record calculus, which essentially combines a lot of existing features, adding a few more, but the combination itself is, to the best of our knowledge, unique. It can successfully track the evolution of the shape and type of the table through different data table API functions. It does fairly successfully verify the invariance mentioned in the benchmarks. It is I would claim, obviously it's subjective, but I would claim this is still a fairly simple type system. There are no qualified types necessary and constraints. But we still don't have a practical implementation, mainly because some questions remain unanswered that are important in practice. That's everything I have prepared for today. Thank you for listening, and if you have any questions, feel free to ask them now or reach out to me under that email. Thank you.